What's up everyone, how's it going? This is Waj, and everybody knows that when you're building a gaming PC, one of the most important components of that PC definitely has to be a good graphics card. It's a solid foundation for any good gaming rig. But in this video, I want to address the issue is how important is your CPU to your overall gaming performance. So in order to address this issue, we're going to compare 4 different CPUs to determine the influence of the processor on different gaming titles that are available right now. Now, importantly, we're going to keep things as consistent as possible. All processors will have 8 gigabytes of RAM. They'll all be using the same exact superclocked version of the GTX 980 from EVGA. And the only thing that will change from system to system is the motherboard and the CPU itself. So if you're interested in seeing how the CPU affects your gaming performance, stay tuned and let's get right into this video. Now, just to give you guys a brief overview of each CPU, we're going to just take a look at the specifications on each processor. Basically, at the lowest end, our AMD 5350 is a quad-core processor that has also 4 threads. Now, the AMD FX 8320 is an octa-core processor with 8 threads. The Intel Core i5-4690K is kind of a mid-range processor from Intel. It has 4 cores with 4 threads. And lastly, the Core i7-5820K is a 6-core processor that has hyper-threading enabled, so that means your OS is going to view it as a 12-threaded processor. Now, in terms of clock speed, each processor is obviously clocked a little bit different. We're starting at about 2 gigahertz on our low-end side. The FX series from AMD starts at around 3.5 and boosts up to 4 gigahertz. And our Intel Core i5 is clocked around 3.5 to 3.9 gigahertz and 3.3 to 3.6 gigahertz on the 5820K. Now, keep in mind that the AMD FX processor and both Intel processors are designed for overclocking in mind. So you can definitely get a lot out of them. But for the sake of simplicity and keeping things as consistent as possible, we're not going to deal with any overclocking. So all of the tests that we're going to show you in this video are done with the stock settings on all of the CPUs. Now, in terms of price always fluctuates depending upon where you are in the world, but basically US pricing right now, currently the Amazon US pricing right now for the 5350 AMD processor is just under the $50 mark. The FX 8320 is about $150. The 4690K is about $100 more than the FX processor, and our 5820K retails for around that $400 USD mark. So you can see that we have a pretty good broad spectrum of what's available right now in the marketplace, both from AMD and Intel. Now, the first thing that we're going to take a look at is the overall power consumption levels on each CPU. And at idle, you can see that the 5350 at idle is certainly the most power efficient at only using around 16 watts, which is very, very impressive. Next, the power consumption goes up quite a bit when you're taking a look at the quad-core processor that's in the Intel Core i5, which uses 44 watts at idle, and the 6-core is around 70 watts, and the FX 8320 is just a little bit more at around 73 watts. Now, at 100% max load, the power efficiency of the 5350 is certainly impressive at only 37 watts. That's pretty much idle for most CPUs out there, so very, very impressive there. And the Core i5-4690 definitely goes up quite a bit at around 109 watts, which is pretty darn power efficient compared to the FX 8320, which is around 181 watts when it's fully maxed out. And our 6-core 5820K is just a little bit over the AMD at around 189 watts. And of course, if you overclock any of these CPUs, expect to see an increase in terms of your power consumption and heat. Now, just to give you guys a demonstration of the performance differences in terms of CPU specific tasks, we're going to use a Cinebench R15 benchmark, which is solely going to test our CPU performance. And basically, you can see that there's a huge variety in terms of performance results over here. As you can see from the results, the 6-core 5820K definitely did an excellent job of scoring over 1065 points versus the Intel Core i5 beat the actual 8-core processor from AMD at around 602, and at the very last place we have the 5350, which only scored a measly 163 points, which is just a tiny fraction of what some of those other processors are doing, and that might really affect the overall gaming performance because there is a pretty big night and day $200K difference between that $50 processor and the $200 and $400 processors. Okay, so now moving forward, we can now finally take a look at my gaming benchmark results on each of these processors. We're going to start with Grid Autosports, which is a racing game, and here you can see by the overall FPS scores, we are getting some variabilities on each processor, even though they're using the exact same graphics card, which is the GTX 980, the exact same overall architecture. Just the only thing that changes between system to system is the motherboard and the CPU. And you can see that pretty much all of the processors are very similar in terms of overall results, basically hovering around that 118 mark, with the exception of the 5350 getting about 82.1 frames per second, which is certainly not bad considering the fact that nobody in the right mind would ever pair a $600 graphics card with a $50 processor, but definitely a good overall performance. Now moving on, Battlefield 4 at completely ultra settings, we're getting around 50.9 frames per second on the lowest end, and at the highest end, Intel Core i7 5820K, we're getting about 90.1 frames per second. So huge discrepancy over here. You can see that certainly a modern game like Battlefield 4 is going to be both CPU and GPU intensive, so you definitely want to have a powerful CPU to go along with your powerful GPU, especially in a game like this. And definitely not bad results from the Core i5 and the 8320, very similar overall scores with the Core i5, just having a slight edge up of the 8320. Next, we're going to take a look at my results for Tomb Raider, which is definitely performing fairly well on all of the systems. The 5350 is getting a very nice respectable score, about 96.7 frames per second, and we are running this game at maxed out settings, and you can see that the other processors are very similar in terms of overall performance, only a couple frames per second apart from each other. Now next, Far Cry 4 at 1080p at high overall detail settings. The 5350 is getting about 48.3 frames per second. The 8350 is getting about 62.5 frames per second. And both the Intel Core i5 and Core i7 are fairly similar at around 76.2 frames per second and 77.8 frames per second respectively. Now the very last title that we're going to take a look at is Middle-earth: Shadow of Mordor. Again, a 1920 by 1080 at ultra maxed out settings. We're basically getting 83.7 frames per second on our lowest end processor, which is very darn impressive. And you can see that the overall variability on this game is not that high at all, so it's certainly more GPU dependent, and you can definitely get by with a lower end processor if you play a lot of Shadow of Mordor, which is definitely nice to see. So you can certainly see that some games will definitely perform better if you have a higher end processor that has more cores and has higher overall clock speeds, but there are certain games like over here you can see where it doesn't make that much of a difference, which is certainly impressive considering the price gap between some of these processors. But that's really it, guys. The overall conclusion is that there are certain gaming titles that are very CPU dependent, and you will certainly get much better performance out of certain gaming titles than others if you have a higher end CPU. But there's many titles out there that just work fine with even a lower end $150 CPU. Now that being said, should you only spend like $25 on your CPU? I think in most cases that's really not the case, and you're certainly not going to pair a really nice graphics card with a really low-end CPU. So you kind of want to mix and match and see where your budget is allowing you to go. Obviously, if you're going to be doing a lot of gaming and you're building a system for a lot of gaming-based applications, you can definitely put more money into your graphics card, and you don't have to really spend that much on your CPU if you're solely making it for gaming. But other than that, guys, thank you so much for watching. If you have any specific questions at all, make sure to leave that on a comment down below. But if you want to know more about each CPU, there are Amazon links in the description, and if you buy anything through our Amazon affiliate link, we get a little bit of kickback. It doesn't cost you anything extra, but you're helping us support the show greatly. Thank you so much for your support again, and we'll see you later. Take care. Thanks for watching.
Welcome back to Computer Hardware, Bits and Bytes. This is an introduction to Unit 3, the CPU. So you're on your computer, and all of a sudden, you need to figure out 93 plus 42, and you don't feel like doing it in your head. So you make the computer do it. But what does the computer do? What happens in its head? For the answer to this question, we journey into the brains of any modern computer, the CPU. CPU stands for Central Processing Unit. You can think of it like a computer's brain, and it works kind of like ours. We'll take a look together at the different structures inside a CPU and connect them to structures we have inside our brains. First off, it has working memory, except called registers. And while us humans can only store 5 to 9 things in our limited working memory, a computer usually has up to 32 things at once. And by things, I mean a collection of zeros and ones, representing a number. So most all the data that a computer processes first must pass through these 32 registers. Second, there is the logical mind of the computer, which is called the Arithmetic Logical Unit, or ALU for short. This is where the data and the registers are actually manipulated. The ALU usually takes two numbers from the registers and combines them in some way. Some of these combinations are mathematical, like add and subtract, and others are logical, like and or. And then it puts the result back into a register. So for any operations that are mathematical or logical, which is actually most of what a computer does, the data will go through the ALU. What happens when us humans run out of working memory? Well, we have long-term memory. In a computer, this is called random access memory, most commonly known as RAM. And when we run out of registers, we can move our information into the RAM. Also, RAM is where most of the memory is located for the current tasks at hand, so we can move it back into the registers for our working memory. RAM, registers, and the ALU, pretty much everything a computer processes flows through these three structures. So these parts of the computer work together to form the basis of the CPU. Let's test your knowledge. Question 1. Can you name the three CPU parts we talked about so far? If you said RAM, registers, and ALU, you are correct. Question 2, related to our example. Where would we add two numbers? The ALU, or Arithmetic Logic Unit, is correct. Nice work. Alright, this is cool, but isn't there some magic missing here? How does the computer know what to do? So computers do all these crazy things and seem really smart, while in reality they are not so smart because they can only do what they're instructed to. So part of the RAM is filled with instructions, which we call the program memory part of it. So all that code that computer programmers write is split up into bite-sized chunks and put here into program memory. It's just like other memory, except that the computer knows it has instructions instead of numbers or letters. So what can we tell the computer to do? All the instructions that a computer has are defined in the CPU's instruction set. There are three main types of instructions. Some use the ALU with numbers from the registers, like add and subtract. Others move data from registers to RAM and back. For example, the load instruction can move data from the RAM to the registers, and store does the opposite. And the last type of instructions change the way that the program flows. So if you add a number 50 times, you can just have one line telling it to do that 50 times instead of 50 add instructions. We'll focus mostly on the first two categories. Now let's move to question 3. How does a computer know what to do? If you said instructions or we tell it to, that's right. Question 4, relating to our example. Where do numbers need to be so that we can add them in the ALU? That's right, the registers, because the add instruction only works from the registers to the ALU. Now let's go back to look at how all these parts work together to solve our little math problem, 93 plus 42. Well, first, these numbers we punched in are somewhere in RAM, except now they look like zeros and ones in their binary version. Still the same number though, and they are in their own spot in memory, labeled FF00 and FF01. These spots are called their address. Yep, almost like they live there. And then we have the RAM, with the two numbers in it at their addresses, and also the registers. So ultimately, to add the numbers, we need them in the registers, right? How would we do that? Let's see if you know. Question 5. How do we tell the computer to move the numbers from RAM to the registers? The load instruction is how we do it. So we tell the computer to move the numbers from memory to the registers by 2 load instructions. So the 93 in FF00 goes to R0, and the 42 in FF01 goes to R1. Question 6. How would we tell the computer to add the numbers? If you said an add instruction, that's right. Remember, the computer can only do what we tell it to. So the next instruction we execute is adding R0 and R1 in our handy ALU. So it moves R0 and R1, adds the numbers, and then outputs it back into the registers. So now the computer has calculated 93 plus 42 and spits out 135. Wow, a lot happened just for one simple thing. And now, you know some of the brains behind the CPU. Hope you stored something from your registers to your RAM today, if you know what I'm saying.